Hello everyone. Today we are going to derive the governing differential equation of a one-dimensional laminar flow system. Before we get straight into the business of deriving the governing differential equation of a one-dimensional laminar flow system, let us ask ourselves this question: why do you want to derive this? So ask this question: why? The reason why we want to derive this particular equation is we can extract a valuable piece of information. And what is that valuable piece of information that you can extract? Well, you can extract velocity. So without having to measure the velocity practically, you can actually get the information of velocity. I have already said that by solving the differential equation, it has tremendous economic utility. So that is exactly the reason why you want to derive the governing differential equation, and you have to solve the governing differential equation to extract this particular piece of information. Now you may ask me this question, by knowing velocity, so what? Well, if you know the velocity, you can find it is a vector actually, you can find the divergence of a vector, you can find the curl of a vector. All these mathematical tools, you can apply all these mathematical tools to find out the rate of flow of water, and you can actually design a system. You can actually design a system for optimum benefit. That is exactly the reason why you want to derive the governing differential equation. Okay, first let me represent the physical scenario here. So I'm going to represent the physical scenario. So the physical scenario is an inclined plane. So let me draw an inclined plane first. So this is the inclined plane on which a liquid is flowing. It may be water, it need not necessarily be water, but water is a very conducive assumption. So these dashed lines represent that a liquid is flowing. Now what I'm going to do is I'm going to entail a set of coordinate axes. So this is going to be our y-axis, and this is going to be our x-axis. So I have just reckoned a set of coordinates. This is x-axis, this is y-axis. Now you would have learned in your fluid mechanics that when a liquid is flowing on this particular inclined plane, the liquid molecules that are in immediate contact with this particular surface, they are not going to move. There is a cohesive force of attraction between the liquid molecules and this particular surface. So the liquid molecules will cling on to this surface, and as a result of which they have zero velocity. But the liquid molecules just above the surface will move slowly, and the liquid molecules above this particular surface will move faster than the layer beneath this particular surface. And the liquid molecule above this particular layer is going to move even faster. The liquid molecules above this layer will move even more faster. Above this layer it is going to move even more faster. Above this layer it is going to move even more faster. So the top layer is going to have maximum velocity. I think you are getting an intuitive picture. So the liquid molecules at the immediate vicinity of the surface, they sort of love the surface, so they are getting attracted to the surface, so they have zero velocity. And the liquid molecules just above the surface, they move slowly, and gradually as you progress towards the top surface, it is going to experience the maximum velocity. Okay, now what I'm going to do is I'm going to consider a small layer. So look at the small layer I'm going to consider. I will use this red pen here, red color. The small layer is what I'm going to consider. So I'm going to localize my attention I'm going to focus only on this small layer. So I'm trying my best to represent the small layer, a three-dimensional view of this small layer. So this is the small layer. At a given instant of time, I'm going to localize all my attention on this small layer. Now, this small layer is taken at a distance of x from the top surface. So the distance from the top surface to the small layer is x. Let us say that the thickness of the small layer is dx. Now you see that there is a quantity of water sitting above the small layer. So this represents the quantity of water that is sitting above this small layer. So the small layer is what we are interested in. So I am just going to shade this at a given moment of time. I'm going to localize my attention on the small layer. Above this small layer, at a given instant of time, there is a chunk of liquid that is sitting on this small layer at a given instant of time. So I'm going to draw the magnified view of this particular physical scenario so that we can understand this concept. So this is the small layer. And there is a chunk of liquid above this small layer. Okay. Now, if you look very carefully at this particular physical scenario, what is driving this liquid in this direction? Well, it is an inclined plane that is inclined at an angle theta. And what should be driving the liquid in this direction is the self-weight of the liquid resolved in this particular direction. So the weight of this particular liquid that is sitting on this small layer, on the small slab of liquid, that weight should act vertically in the downward direction. So that weight of this particular liquid, the slab of liquid, that weight should act in the downward direction. That weight is W. That is acting in the downward direction. Now, the distance between, okay, so you see that the action force is the weight resolved in this particular direction. And what is the resisting force? The resisting force is offered by this shaded area here. So this shaded area offers the resisting force. And what is that resisting force? It is tau into A, where tau is the shear stress. Now, how do I get this particular formula? Well, we already have shear stress is equal to shear force divided by shear area. So you work out for shear force, that becomes tau into A. So that is how we get this resisting force. So now you have got an action force, which is W cos theta, which is weight resolved in this particular direction. And you have got the resisting force, which is offered by this shaded area, and that is tau into A. Now I am going to invite a person. That person is Sir Isaac Newton. I have got a photo of Sir Isaac Newton. So I will just show his photo here. So an inspirational figure. Okay, Newton's third law. I think everyone would remember Newton's third law. And what is Newton's third law saying? This action and a reaction, they should be equal, but they should be opposite. So you have to introduce a negative sign when you equate these two. So I'm just going to equate these two. So inviting Newton, W cos theta is equal to minus of tau into A. Okay, now action is equal to negative of reaction. I just got this information from Newton's third law, just leveraging that information from Newton's third law. Now what I'm going to do is I'm going to localize my attention on W. So localize your attention on W. What is this W? That W is weight of this chunk of liquid. And you know what is weight? Density You know what is this weight? Okay. Density is equal to mass by volume. So what I'm going to do is I'm going to multiply by G on either side. So it becomes rho G is equal to mass into G divided by volume. Since I'm multiplying by G on either side, I actually do no damage to this particular equation. So rho into G, sometimes people call this as weight density. But what is m into G? Mass into acceleration due to gravity. That is weight divided by volume. So rho G is equal to weight divided by volume. If that is the case, then weight is equal to rho G into volume. So I'm going to plug this particular equation here for W. So take this object and put it here and see what happens. But before I do that, I'm going to localize my attention on this particular tau. Now what I'm going to do to this tau? Well, I'm going to get that information from this person, Newton. He has given us a law, that is Newton's law of viscosity. And what is Newton's law of viscosity saying? Tau is equal to mu into dv by dx. That is Newton's law of viscosity. Now, how do you get this particular equation? That is a different video. That is for a completely different video. But this information is from Newton's law of viscosity. You should have learned fluid mechanics. In fluid mechanics, you see how we derive this particular equation. That is, shear stress is directly proportional to rate of change of shear strain. In order to eliminate the proportionality, you have to introduce a constant, and that constant is mu, and mu is popularly called as coefficient of viscosity. Okay, now I'm going to substitute the value of W, which is rho G V into cos theta, where V here stands for volume, is equal to minus mu into dv by dx into A. In the next step, it is going to be rho into G. What is volume? Volume of this particular chunk of liquid. And what is the volume of this particular chunk of liquid? It is this area into this height. That will give the volume. This area, shaded area, that shaded area is A into X. So that should give the volume. So volume is area into X into cos theta is equal to minus of mu into dv by dx into area. You can cancel the area on either side. You'll be left with, you can take this mu dv by dx, throw it on the left side, and let us see what comes. It is mu into dv by dx. If you throw it on the left side, this negative becomes positive, plus rho g x into cos theta is equal to 0. all you have to do is differentiate this particular equation with respect to x. What is that you are going to get? You will be getting mu into, if you differentiate this particular equation with respect to x, d squared v by dx squared. You are differentiating with respect to x, so differentiation of x with respect to x becomes 1. So it is rho g into cos theta is equal to 0. That's the governing differential equation. That is the governing differential equation. Sorry about this. That is the governing differential equation of your one-dimensional laminar flow.